Okay, that was very good. Two very nice studies that were completed over the course of the last year. We hope to write those up and have them published within the next year or so. We'll move ahead now. We're back on time schedule to Rafi Avedian, who was one of our residents at UCSF and went on to a fellowship in orthopedic oncology at the University of Chicago. And now we're very proud to have him as a colleague as an assistant professor at Stanford University in the Bay Area, and he's going to talk about a more of a basic science study. It's very exciting to see these additional studies being done in addition to the clinical work that's ongoing.
Well, thank you very much, Dr. O'Donnell, and thank you very much also for the opportunity to speak here and present some of our research. To start off, I'd just like to acknowledge some other people that helped with this project and my co-authors. Timothy Chen, he's an undergraduate student from Vanderbilt University, and I'd also like to make note that this work was done mostly at the Veterans Hospital in Palo Alto, and acknowledge their help in giving us access to the biomechanics lab. I don't have any conflicts of interest as related to this project. And we've heard a lot about the compress today. And as many of you know and has been discussed, traditional stemmed implants have functioned very well, but there's concern about aseptic loosening and other modes of failure, which has led us to the excitement about the compress implant. And at least in the short term and intermediate term, a lot of the results are at least equivalent to stemmed implants, if not better. However, there is some concern about failure, at least in the short term, and this is a good example of that. This is a 60-year-old gentleman who had a distal femur chondrosarcoma, actually a patient of my partner's, and you can see here he was doing very well up until about 3 or 4 months, and then he leaned down to tie his shoe and felt a pop. And we got this radiograph here, and it's actually an AP of the knee, and you can see, excuse me, you can see here, this is pretty much an AP of the tibia, and you don't see the pelvis, but that's also an AP. However, there's a rotation here at the distal femur. He actually spun about 30 or 40 degrees and then re-engaged, and he actually had no pain after this, but his leg was externally rotated. He went on to a revision and did very well. However, obviously there was some concern about rotation. And so there's been a lot of discussion about using anti-rotation pins to help overcome this problem. And you can see here a newer design of the compress with, excuse me once again, multiple pin sites so in order to put the anti-rotation pins in locations that you can engage the bone. So we decided to study this, and we asked the question, does the addition of anti-rotation pins improve rotational stability at the bone prosthetic interface? And what is the effect of adding sequentially increased number of pins? And then what was the mode of failure? So we obtained 8 matched pairs of formalin fixed femurs. They all underwent DEXA scanning to determine their bone mineral density. We osteotomized each of these femurs at the mid-diaphysis, and therefore we had about 32 specimens for evaluation. We, as I mentioned, we cut all these femurs in half, so each femur gave us 2 specimens, and each matched pair gave us 4, which are essentially identical femurs. And by doing that, we were able to uniformly distribute some of these femurs across the test groups. So group 1, we had 4 femurs that had no pins, and we compared those to 4 femurs that had 1 pin. Group 2 was 1 versus 2. Group 3 was 2 versus 3, and group 4 was 3 pins versus 4 pins. So each specimen was potted into the metal container that you can see here with acrylic cement. The exposed end of the compress, or the exposed end of the femur, was prepared with the face reamer that, according to standard technique, and you see the instruments back at the table there. Then the spindle was mated to the servo-hydraulic device here. And then the appropriate centering sleeve was placed onto the compress, and the compress was inserted into the femur. And with this device, we were able to apply 600 pounds of force. We chose 600 pounds as that was what we most commonly use in our clinical practice. Pins were inserted according to the test group, and based on our preliminary studies, we found out that the pins need to be fully engaged into the bone. In those cases that we did our practice runs where the pins were just superficially in the bone or were not fully engaged, they would spin out and cut through the bone. So we did that uniform across all the test specimens, that the pins were fully engaged, and that was uniform across the groups, as I said. Torque was applied with the MTS device here. We set the machine to apply 1 degree of rotation per second, and the machine therefore would generate whatever torque necessary to accomplish that, and that torque is what we are recording. So here's an example of that. We can play the video here, which actually doesn't run. Can we play the video, please? Yeah, thank you. Okay, go ahead. So this is 600 pounds with 1 pin. You can hear the crack, the femur's fracturing. Here's a fracture line developing. Sorry, it's a little blurry. Yeah. Here's the fracture. Then we turned it off, so that's when it rotated back. And so we analyzed the result of that run. So torque on the y-axis and the rotation as the x-axis. You can see that as the rotation was applied, there was actually, from the very beginning, a little bit of rotation. And then that was essentially a linear rise in the torque necessary, and then it fractured, and then it plateaued. And this was about I'll show the results of the actual torque necessary, but this one was at 20, but most of the ones with no pins were lower. Here's an example. This is with, so no pins. So it has not engaged yet. You'll notice that it's being lowered down onto the femur here. And the rotation is being applied. And it's subtle, but you can see the rotation occurring here. And so this is what, when we graph torque versus the amount of rotation, and again, there's a steep rise in the torque necessary to achieve the 1 degree of rotation. It reaches here, and then when sorry, these graphs are backwards, but this is the one with the 1 pin. So the one I showed before was with the no pin. So the video that I just showed was no pins, but you could see that the rotation went from, the torque necessary for rotation was a steep rise, and then probably what happened here without the pin went from the static coefficient of friction, which is essentially higher friction, and then when the motion started occurring, that went to a dynamic coefficient of friction, then it just started spinning a little bit more easily. And then with the 1 pin, we had the steady rise in the torque necessary to achieve that motion. Even with the 1 pin, there was some small degree of motion early on, and then the fracture occurred, and then you have this irregular relationship between the torque and rotation, probably with continued fracture, then settling, and then more fracture, and then you end up with this variability in the torque necessary. So sorry about that, I had that mixed up. And here is just a plotting of the data we got with a 4 pin. Essentially looks the same, except you notice that more force was necessary or more torque was necessary to achieve the rotation, and this failed also with fracture. These are the results plotted out by in a chart form. So group 1 over here, so no pins compared to 1 pin, that was statistically significant here. And essentially the torque necessary without any pin to achieve the maximum torque necessary was about 14 Newton meters. And you'll notice here with 3 pins, and 4 pins, essentially in the high 30s to low 40s, and the machine was set the highest that we could measure was 45 anyway. So 3 and 4 pins had a very high degree of rotation necessary to achieve the motion. And plotting it out as a regression analysis, so these little X's represent each specimen, so 0, 1, 2, 3, and 4 pins, and essentially a very linear progression in the torque necessary to achieve the rotation, and that was very significant. But again, 45 degrees was our upper limit of our machine, and so we approached that with the 3 and 4 pins. So our modes of failure were, with the pins in place, was by fracture. This is with 1 pin. You'll see a longitudinal split in the cortex, and then when we took this off, 180 degrees opposite that was another fracture, so just essentially 2 longitudinal fractures. And we saw similar findings with the multiple pins as well, essentially fractures at the pin sites. And without the pins, there was just a rotation at the interface. So in conclusion, antirotation pins do appear to increase the force necessary to have rotation occur at the bone prosthetic interface. Each pin does improve, each pin does increase the force necessary, which is, I think, intuitive. The modes of failure were slippage or fracture at the pin sites. Each additional pin decreased the likelihood of fracture, and we need to have more torque to achieve it, to see the fracture. And that's likely because each pin distributed the stresses more evenly across multiple sites, so less pressure at each, or less stress at each pin site. But it's worth noting that pins are not a substitute for good technique. A nice even bone cut with uniform application of the compress onto the bone. And the pins should be placed well into the bone when you do that. So we compare this to some of the studies in the literature. This is a nice study back from 1998, Journal of Arthroplasty. They did actually distal femur replacements, oncologic prostheses, placed strain gauges in the prostheses and did in vivo studies. And you can see that the torques with various activities such as walking, going up and down stairs, getting up out of a chair. The highest torque was around actually 8.1 at walking and then 7.9 getting out of a stair. So these are the actual real torques in vivo. And with our formalin fixed femurs, so very bad femurs, very osteoporotic, not very strong femurs, we were getting up to 8, 12, 10 Newton meters without the pins. And fractures were higher than that. So that's a good safety of margin of safety. So the conclusion, are pins actually necessary? We've seen several case examples without any pins, and people are doing very well. It's a little bit of a judgment call. I think more studies need to be done, obviously, to really evaluate this. But in my opinion, I think many people would agree that pins do improve the stability at the bone prosthetic interface. They're very easy to put in. There's very low morbidity associated with it. And in the cases that there are failures, this may be able to prevent those from happening, such as the case that I showed earlier on. So just point out some limitations of our study. Obviously, it was a biomechanical study, so the forces that we generate are not necessarily reflective of what's happening in vivo, and that's true for any study. We don't take into account soft tissues, rehab protocols, activity modifications, and so forth. Our torque gauge was limited to 45 Newton meters, so the 4-pin samples may actually have been higher, but we just weren't able to measure that. We didn't test 400, 600, and 800 together. That's what you can put a compress in. Just for fun, I did run a few samples with the 4 and 800. The 4 would spin at around 5 Newton meters. I only did one sample like that. And the 800 was up to in the mid-20s, the one that I did. So it's kind of a linear progression at first glance. So thank you very much.